want to thank everyone for attending today's iteration of our Minds, Technology, and Society seminar that's sponsored by the Glushko and Samuelson Funds. I want to thank you all for attending the talk, given that today's speaker is an internal speaker. And also just a reminder that our speaker for next week will be Heather Dean from the U.S. Department of Food, Drug, and Administration. And so just one very, very minor housekeeping thing is that basically I am using for the first time a pointer, and our colleague Carolyn Jennings was nice enough to let me use this because I asked her for it, and I haven't become quite adept at it, but I'm having so much fun with like a new toy. So even though I'm not all that adept with it yet, I'm going to use it anyway. But just to let you know, I may be drifting back and forth because I discovered that this device actually enables you to see one of the screens ahead of time. So all that basically said, I may be bobbing a bit back and forth, which will irritate Tim no end, but that's just how I'm going to be. So the topic that I'd actually like to talk about today, the title Inductive Learning and Bargaining Conventions, which is part of my long-time research interest in convention. And I'm a philosopher by training, and in my opinion, philosophical analyses of convention are a recent phenomenon. So I can find discussions of convention in philosophy going back before Plato, but in my opinion there is no serious attempt by a philosopher to actually try to analyze what a convention might be until 1740, which for philosophy timeline is real recent. And so that's one of the reasons why I've gotten very hooked on this topic, is that I think that convention is a latecomer or late bloomer in philosophy. And also convention is an area that can be analyzed. Philosophers have tried various approaches to it. I take what now is maybe the most well-established approach, was I try to connect convention to game theory. And I've gotten very interested in what I consider a very recalcitrant problem in game theory that's known as the bargaining problem. So I'll go back to that. I always, okay, is it going to go? There, all right. I always begin with an epigraph, and this is taken from Aristotle's Politics. So this is basically a representative, right? Oh, and I forgot to mention, by the way, I welcome any questions along the way, because I know that I have, somewhat by design, I haven't included as much of the technical details in the slides as some of you might be expecting. And so if there are questions along the way, please go ahead and halt me. But the epigraph taken from Aristotle is, all men think justice to be a sort of equality, for they say what is just for someone, and that it should be equal for equals. But there still remains a question, equality or inequality of what? And here is a difficulty which calls for philosophical speculation. And so the claim that Aristotle makes, and he makes this in various places, including the quote right here, is that he alleges everyone agrees on a formal principle of justice, which is equals are supposed to get equal shares. And then he claims that the reason that we have these protracted disputes about justice is that we argue over the relevant criteria of justice. But in my opinion, there's this equality principle or proportionality principle itself is a matter for philosophical speculation, because I'm going to claim that this principle, even though allegedly people, according to Aristotle, everyone appears to agree upon it, it doesn't follow from the logic of rational choice. Okay, and so to try to motivate this, I basically look at what's known as the bargaining problem. And the bargaining problem was formally introduced in the early 1950s by John Nash. And in my opinion, it's one of the two central contributions that Nash made that won him his Nobel Prize in 1994. And Nash did have some intellectual predecessors, as Frederick Zeuthn basically analyzed a special case of the bargaining problem in the 1930s. And I'm going to show you in a minute an example from David Hume in his treatise, which is a bargaining problem involving three individuals that are having a dispute over dividing a quantity of wine. And there's actually a proto-bargaining problem in the Talmud. So there's what's called the contested garment problem, where you have two individuals who are claiming shares of a garment. And in philosophy, the bargaining problem has, in my opinion, something of a checkered history. It kind of falls in and out of favor, and it seems to be rather deeply out of favor these days among philosophers. But Richard Braithwaite actually he defended a particular solution and used the bargaining problem as a foil for analyzing problems of distributive justice in a lecture he delivered in 1954, published a year later. And then David Gautier, recently retired from the University of Pittsburgh, basically he tried to construct a principle of justice, again, using the bargaining problem, and I'll illustrate Gautier's analysis of it as we go along. And then a little more recently, also recently retired, Ken Binmore did in his large treatise, Game Theory and the Social Contract. He largely bases his theory of distributive justice using the bargaining problem. Right? And a way of characterizing the bargaining problem could be described as follows, that you have basically a group of n agents, and these agents are each trying to claim the share of some good that's in fixed quantity. If they issue compatible claims, and by that I mean that they basically, each one basically issues a claim, and then there's enough of the good available to issue each agent the claim that she asks for. When the claims are compatible, then each agent leaves with her claim. But if the claims are not compatible, then the agents arrive at some non-agreement point that reflects their conflict. And typically, at the non-agreement point, each agent will receive nothing at all. That is a zero share of the good at stake. Okay, and okay, try again. Did it go? Okay. So here's the first of several examples. This is David Hume's example, and I'm quoting from Hume. Suppose a German, a Frenchman, and a Spaniard come to a room where there's placed upon the table 3 bottles of wine, Rhenish, Burgundy, and Port. And suppose they should fall a-quarreling about the division of them. All right? And so Hume, in fact, goes on to give what he considers basically a solution to this dispute. There it goes. So see, here's a bottle of Rhenish, German wine, bottle of Burgundy, French wine, and a bottle of Port. And so the bargaining problem in this situation, there are 3 claimants, and the 3 claimants each would like to claim a share of the wine at stake. And the background assumption is each of these 3 claimants can drink a lot. There it goes. Then another example, which I'll be talking about several times in the body of this talk, is there are 2 hungry claimants, Claudia and Laura, and there's a chocolate cake that they have available to them. If they can issue compatible claims on the chocolate cake, each can have what she claims. But if their claims are incompatible, then the cake will dry out while they're bickering over their incompatible claims. And a third example, if it'll advance. There you go. The third example actually is also very simple. So this is basically referring to an experimental study that was done in the early 1970s by Rudy Neidegger and Guillermo Owen. And what they did was they had basically groups of 2 German students. They would have 3 groups of 10 each, and basically there were 30 pairs of experimental subjects in their study, and what they were basically assigned to do, each of these 30 pairs, was very simple, that each of them was basically, I'm told, you need to issue, each of you independently, a claim on some share of $1. And if your claims are compatible, then each of you will get your claim. And if they're incompatible, you both get nothing. And so what happened was that, in fact, in all 30 of these pairs, all 30 pairs basically came to exactly the same outcome. And that is, each one of the 30 pairs ended up where each of the two claimed 50 cents. And it's my understanding that this now classic study at the time didn't get a lot of attention, and the reason seems to be that no one thought the result was surprising. There we go. So what I want to show now is the way that Nash characterized the bargaining problem. What he did to make he basically created a formalization of the bargaining problem where it's characterized by, first of all, what's called a feasible set. And here is a sketch of an example of a feasible set that is basically the green areas basically correspond to all the possible payoff vectors or payoff combinations that two individuals can get. There it goes. All right. Okay, it's a two-agent bargaining problem. The vertical axis will always correspond to Laura's claim, and the horizontal axis will always correspond to Claudia's claim. And what you get here is, again, the green points are all the possible joint payoffs that they are capable of arriving at. And just so you can see how this works, this upper one right here, okay, the point 1.5, okay, this is where Laura claims all the good at stake and Claudia claims nothing. Okay, this point right over here, this is the point here, I believe it's 1 2/9, where Claudia claims all the good at stake and Laura claims nothing. All right, and then all along here, okay, this line segment joining those two extreme points, those are all the possible divisions that are in equilibrium, and I'll explain why they're in equilibrium in a little bit. But then there's all sorts of other outcomes that they might arrive at. Okay, again, the green payoff region you might think of as all the possible outcomes corresponding to compatible claims. And then the non-agreement point, that point marked in black there, that corresponds to what happens if they fail to arrive at agreement. And so this is basically this black dot corresponds to an outcome where both of the claimants, in fact, get none of the good at stake. Okay, so this is just one example, right? Oh, whoops. Okay. And so I want to actually first describe the approach that I don't take to looking at this problem myself, but it's if you will, in my opinion, a better known approach. I call it the a priori approach, and it's the approach to analyzing the bargaining problem taken by John Nash when he first introduced the problem, later by Richard Braithwaite, the philosopher, and David Gautier, the philosopher, and then Ariel Rubinstein, the economist, and they're basically one of basically a whole large community of people who've tried to analyze the bargaining problem in what I call the a priori method. But and basically what in my opinion, the way that this works is to basically approach the bargaining problem assuming that all the agents are basically coming to the table having basically what you call common knowledge of all the payoff structure and common knowledge that they all choose rationally. And by that I mean each one of the agents is choosing so as to maximize her expected payoff, given what she expects the others to do in the situation to choose. And then you can basically pick what is called an axiomatic solution to the bargaining problem that will satisfy special structural properties of this problem. Or you can basically also look at what rational agents would do if they basically approach the problem via a process of strategic bargaining. And so there are a great many proposed axiomatic solutions to the bargaining problem, and in fact you can actually have, there are books actually that describe in great detail entire families of axiomatic solutions to bargaining problems. And all these bargaining solutions have certain good characteristics to them. In my opinion, the most widely endorsed of these bargaining solutions are what is known as the Nash solution and the Kleist-Mordetzky solution. And if I can get it to advance, the next slide shows you. Okay, right. This is why I wanted the pointer, everyone, because I sketched out as best I could in the example I had before. If I can get it. Okay, here we go. The left-hand side basically is a way of illustrating the Nash solutions. The Nash solution to this bargaining problem is where I've got the pointer right here. Okay, and basically what you have, it'll come back, there we go. You notice I've drawn several rectangles, basically, and one vertex of the rectangle is at the outcome of non-agreement, where both sides get nothing, and the other vertex of the rectangle touches this line segment here, where the good at stake basically is shared out fully. Yeah?
Peter, what are the axes here?
Okay, so the axes again are, horizontal axis is the row agent or Claudia's payoff, and the vertical axis is the column agent or Laura's payoff. It's a two-agent bargaining problem.
So how can they sum to greater than one?
They can't. It's like this is all right. So the maximum payoff either can get is one. I'm sorry. So this is not basically reflecting absolute amount of good. It's reflecting the utilities that each gets, and the utilities are scaled so that the lowest utility each can get is 0, and the highest is 1. Okay. So at this point here, all right, Claudia would get all the good at stake, and that corresponds to a payoff of 1. Okay, the amount of good that Laura gets corresponds to her getting a payoff of 2 ninths. Okay. And I'll show you the matrix in a little while that gives you the basis for this particular game. This, by the way, this example I'm using is the game that Richard Braithwaite used in his lecture, which has become somewhat famous in philosophy because it seems on the surface to be somewhat simple, but it's surprisingly hard to actually analyze it. Okay, the point right here again, this point 1/2, Claudia gets a payoff of 1/2 and Laura gets a payoff of 1. Okay, this is the case where now Claudia gets none of the good at stake and Laura gets all of it. Okay, and I think maybe what's bothering some of us is, right, this basically, the payoff structure reflects the idea that this is what's called an impure coordination problem. And so it's not basically a case where the payoffs are determined uniquely by or I should say this, that the payoffs basically are not entirely independent of what your partner receives. So even if you receive nothing, like Laura receives nothing here in this board, she still gets some satisfaction. It's better for her to be at this outcome where at least she gets nothing, but Claudia at least gets something. Then over here, if they both try to claim everything, they both get nothing, and they both regard that as less desirable than. I wanted to mention, by the way, I said a couple of times already, this line segment, it corresponds to the equilibrium points that you can have in the bargaining problem. And you can think of it like this, that at any one of the points along that line segment, right, if, for example, right, you're at this point right here, which is the point that's the so-called Kleist-Mordetzky point, the row agent basically can't do better by claiming more, because if the row agent claims more, they both get nothing. If the row agent claims less, the row agent would be putting herself over here and then basically getting strictly less. Okay? And similarly, if the column agent were to try to claim more, the column agent would basically get nothing. And if the column agent claims less, the column agent would be down in this gray region here, getting strictly less. So does that make sense, actually, to why I'm claiming this is... So in other words, the basic idea, this is what's sometimes called the Pareto frontier of the bargaining problem. And the easiest way to think about it is nothing goes to waste. There's no unclaimed good left over at an equilibrium point. And this is why the bargaining problem is a challenge, is because there are literally infinitely many different bargaining points, different equilibria. Yeah.
Sorry, I just missed. Why does them both getting nothing correspond to 2 knights?
Oh, right. Basically, that's because in this particular game, right, both of them getting nothing is Claudia's worst outcome, but it's not Laura's worst outcome. Right? So there is an asymmetry in this particular example, and this is basically this is formally this is called that Laura, the column player, has what is called formally a threat advantage, because Laura is willing to be she's basically thinks that the non-agreement point where both try to claim everything is less bad for her than it is for Claudia. It's Claudia's worst possible outcome in the whole game, right? And by the way, so you see these 3 different rectangles? Okay, the Nash solution corresponding to the black rectangle. The Nash solution to this bargaining problem is defined as the equilibrium outcome that characterizes the largest rectangle. Does that make sense? That every one of the equilibrium outcomes will characterize one of these rectangles. So right here, this equilibrium outcome, it characterizes that red rectangle. This one right here characterizes this green one. And then, so all the equilibrium outcomes will basically define an entire family of rectangles, and the rectangle that maximizes this product right here, the maximal area, the largest area, that defines the Nash solution. Okay, and if you did, if you note, I should, one comment to make about this. You notice how the Nash solution, how close it is to Laura's favorite outcome where she gets everything. So just as a side comment, at the Nash solution of this particular game, basically Claudia gets 1 of 14 shares of the good at stake, and Laura gets 13 of 14 shares. So it's very favorably biased towards Laura. Okay. The Kleist-Mordetzky solution over here, right? Just to see how this is constructed. Okay. Basically, here's the non-agreement point. This point here in this rectangle I've had. This is the so-called ideal point that basically would occur if somehow each of the 2 agents were to receive all the good at stake, everything she could possibly claim. The 2 agents cannot achieve that point, okay? And then the Kleist-Mordetzky solution basically says you construct the line segment that joins the ideal point to the non-agreement point, and you pick the intersection, the equilibrium at the intersection. Okay. Yeah.
Why?
Okay. Right. Basically, neither of these solutions, in my opinion, has a very good intuitive foundation. Right. What the defenders, like David Gaudier of the Kleist-Mordetzky solution, propose is they say, at the Kleist-Mordetzky solution, each agent basically gives up the same relative concession from the ideal point. Okay. So, right, and if you're looking at me like, okay, yes, it doesn't sound that intuitive. I'm going to gripe more about this in a minute, right? I actually find the Nash solution even harder to get my head around, because, as I said a minute ago, the Nash solution is characterized by the largest of those equilibrium rectangles. And you go, well, what's so nice about a large rectangle, the largest of all possible rectangles? It's not on the surface clear why either of those solutions seems to be so good until you look at the structural properties that they satisfy. And so, all right, if you don't, I'll go ahead. So I'm going to bring back those examples in a minute, but the axiomatic, the a priori approach, in my opinion, has its limitations. So the axiomatic approach, and I showed you two of the most prominent solutions just a minute ago of the axiomatic approach. It shows every bargaining problem has a unique solution. That's a big uniqueness is a great property, and it satisfies several of a set of intuitively appealing properties. Okay, so if I bring it, all right. So for example, both of these two solutions, Nash and Kleist Mordetzky, they are equilibrium solutions, and they are so-called, basically, they satisfy the principle of optimality in the sense that, again, nothing is left to waste at either of these solutions. So at least they have that much going for them. And another property that they satisfy is what is called scale invariance. It won't come back to me. Okay, here we go. Both of these solutions satisfy what is called scale invariance, and by that I mean that if you basically change the payoff scales by translating them the way you would translate a temperature scale, if you change the temperature, change the payoff scales by multiplying each of them by a constant that's positive and adding some constant to them, the solution itself doesn't change. The solution will basically give each the same shares as before. So, all right, so it satisfies those good properties. However, basically, none of the axiomatic solutions will satisfy all the properties that you'd like it to satisfy. Okay, and so if you want to go back, I don't know, maybe I should bring back the picture I got a second ago. One more time. So here is what happened. What's basically a defect of the Kleist-Mordetzky solution. And that I don't have a picture to illustrate this with, but I can describe it quite simply this way. All right? The Kleist-Mordetzky solution is not stable when you basically reapply it with more than two claimants. So to describe this informally, if you have three or more claimants of the good that's at stake, and then you apply the Kleist-Mordetzky solution to all three or more, okay, and then you share out the good, and then some subset says, oh, we want a recount. Okay, so some subset, say two of them say, all right, we want this solution applied to us and basically checked over. Okay, the solution won't yield the same results. It's unstable with respect to reapplication across subsets of claimants. Okay? The Nash solution has a different kind of instability. Okay? And so the Nash solution basically has the following defect. Suppose that the feasible set is basically made larger. So there's more of the good at stake than there originally was. Okay? Now, if there's more pie to share out, you know, like when I do this in classes, I know it's not so edifying, but like I said, what if we had a pitcher of beer? I'm going to share this out, and the students are all looking at me like you're not really talking about beer, are you, Peter? It's like, yeah, I'm talking about beer. All right, and if all right, but then I said, all right, well, we basically say we'll apply this Nash solution to the quantity of beer. And we share out the beer, and they say, oh, guess what, everyone? There's some more beer to be shared out. More than original. Well, what one would think, if the amount of original good is expanded, then no one should receive less in the end than what she would have received originally with the smaller quantity. But in fact, the Nash solution doesn't satisfy this property. The Kleist-Mordetzky solution does, but there you can basically have a case where you increase the amount of good and the Nash solution gives someone in the group less. Okay. So basically, in my opinion, if you follow David Gaudier and Richard Braithwaite and John Nash and you try to use axiomatic solution concepts alone, basically you're going to have to, I put it this way simply, you have to pick your poison and decide which sort of solution instability you're willing to live with. All right? And then I didn't give a pictorial example of this, but basically but the alternate approach, which basically it's closely tied to the axiomatic solutions. It's another route to the axiomatic solution, if you will. If you try to look at the bargaining problem as a sequence of alternating offers between agents who are ideally rational and have common knowledge of their ideal rationality and their payoffs, right? Then you can only get a definite result for a very narrowly defined class of bargaining problems. It only works for bargaining problems with two agents, and the good at stake has to be infinitely divisible. So for instance, the alternating bargaining solution would not yield determinate results in the divide the dollar game, because when you divide a dollar, how many possible ways are there to divide the dollar? It's only down to a cent. So it's not actually an infinitely divisible good. And so in that context, the alternating offers approach doesn't yield any determinate results at all. And similarly, when you have three or more agents in the alternating bargaining process, that doesn't yield determinate results either. So basically, I'm through bad-mouthing the approach I don't follow. Right? So the approach that I've explored is basically what I regard as a lesser explored approach that I think I attribute to Thomas Schelling, who recently deceased, Nobel laureate in economics, and before him David Hume. Right? Even though Hume didn't have the vocabulary of the bargaining problem, Hume has simply amazing observations about division problems. And my very senior colleague Bob Sugden at the University of East Anglia. And the approach that they basically endorse, and I actually am trying to follow in it, is one can interpret the solutions of a bargaining problem as conventions. And so by a convention, I mean one of many different equilibria. Right? And right, you can interpret this as conventions that agents who aren't ideally rational, but boundedly rational, could learn to follow by a combination of inductive learning and what are called focal point effects. Okay. And so what I'm arguing specifically, and this I actually, this I think is new stuff. I argue that a focal point and learning approach, it's not going to be giving deterministic results, and that's not, you wouldn't expect it to, but it lends some support to the relatively neglected solution that's known as the egalitarian solution. And I'll give you an illustration of that one right here, okay? The egalitarian solution for that generic problem is right there. And the egalitarian solution, it's gonna come up. Okay, there it is, the egalitarian solution. The egalitarian solution turns out to be equivalent to that Aristotelian principle of equal shares for equals. And a way to look at it in this particular example, it's very, very simple. All right? This is a square that I've read. And so the egalitarian solution simply reflects the point at which both of the two claimants get equal gains from the non-agreement point. Sounds very simple, and it actually is very simple. The egalitarian solution, basically, it it has that property that we want to have that I hinted at, that it's stable when it's applied across groups of 3 or more. You can basically apply it as many times as you want to, and every possible reapplication will give the same result, so that's kind of nice. And it's also stable with respect to expansion of the payoff set, so that sounds kind of nice, and so it has these very desirable properties. You might be asking yourself at this point, well, if it's such a nice solution, why is it so undervalued? Yeah.
I'm sorry, just one more clarification. So just from looking at this, so the payoffs are not identical and the utilities are not identical.
Right.
So how is it determined?
Okay, it's determined by, all right, the payoffs aren't identical, but actually, Paul, you know what, you just actually pointed me to why this solution gets less attention than I think it might. Okay, because this solution actually does have, I think, an intuitive underpinning that sounds like, okay, here we go, right? Here's the payoffs the two of them get at the non-agreement point, and each line segment here basically goes up here. This square basically is trying to indicate at this point the egalitarian solution. Both sides have made an equal gain in their payoffs from where they would have been at the non-agreement point. But by saying equal gain in payoffs, I've actually basically said in not so many words, you can compare the payoffs of the various claimants and identify a solution where they get equal gains. Well, maybe I should bring the picture back a second, because this introduces, so basically what you have here is the egalitarian solution, in fact, incorporates what are known as interpersonal comparisons of utility across the claimants. So the idea is that, again, each one of the agents, basically, the gain that she receives in payoff can be compared to the gain that the other agents receive. And this is basically this is reflected by the idea that the egalitarian solution doesn't satisfy what I referred to before as the translation invariance. That if you rescale the payoffs in certain ways, okay, the solution might change, right? And so the issue of the question, I should say, of interpersonal utility comparisons has produced polarization that, in my opinion, it's analogous to the debates in philosophy about libertarianism versus any alternative to libertarianism, or determinism versus free will, right? That basically each side of the debate is extremely adamant, and the sides of this question are very polarized. And so, and it's similar among the social scientists, that there are many social scientists and philosophers, and John Nash was one of them, who said that you cannot basically, in a non-arbitrary way, compare utilities across different agents. And so Nash tried to short-circuit this in his own discussion of the bargaining problem by requiring translation invariance, which amounts to saying no interpersonal utilities of interpersonal utility comparisons. Right? There are others who I think are in a minority, and John Harsanyi, the Nobel laureate, he might have been the most eloquent of these, who said that, as a matter of fact, we humans are making interpersonal utility comparisons in a rough manner all the time. We do it all the time in our interactions with each other. It guides our conduct because we think that by what we observe in others, that we can draw conclusions about what will or won't satisfy their preferences. And so we do it all the time, says Harsanyi. The question is there a way of doing this that has a firm logical basis? and the debate kind of continues. But I just want to say that's what I think is at stake. And so the egalitarian solution, in my opinion, has been a neglected solution concept. But I maybe just as a real side comment, many of you who haven't known me as long as, say, Jeff or Ramesh or Tini have known me, right? I change my mind a lot. And I have changed my mind so many times about the bargaining problem. It's like, I feel like I'm finally settling down into a kind of equilibrium about it. That I finally have actually decided I'm in favor of the egalitarian solution. Go figure, after years of having been going back and forth between Nash and this and that, right? But what I have tried to do, and I'll try to explain why I think this is novel in a little bit, is I apply an inductive learning rule to the bargaining problem and see what agents who learn according to this inductive learning rule might arrive at. And so this is the formula that we have right here in the middle of this slide defines what is called the rule of weighted fictitious play. And the way that to think about this is that learners who learn according to this rule, and incidentally, because I know a number in this group look at learning rules like reinforcement learning. Okay, this is sort of a fellow traveler learning rule that you could say. So just to for those who might want to actually look at this in another time, that one unanswered question is, I don't know what would happen if you applied only reinforcement learning to this kind of thing. This kind of inductive learning is what's sometimes thought of as basically simple utility maximizing given your current conjecture or belief. And so the idea is this formula in the middle basically defines this mu basically for a player I, a claimant I, at a period t plus 1, okay, is this agent's probability, her probability that her counterparts will follow a particular strategy profile, and that's boldface S sub minus I, and it's going to be a weighted frequency of the number of times that she has observed her counterparts follow this profile. Okay, so basically I've given for you the recursive version of this inductive learning rule, and one comment to make about it is basically, or two actually. One is that this is a generalization of an account of inductive logic that was proposed by the great philosopher Rudolf Carnap. Okay. Another comment to make about it, what makes this different from an inductive learning rule like Carnap's is there's a bias toward the recent past. That's why it's called weighted fictitious play. So those thetas, basically, those represent how much you weight the observations you've observed in the most recent time, right? And so this kind of learning has been tested in the laboratory where they have agents who actually play coordination games literally, and they try to basically figure out which learning rule models their learning the best, and weighted fictitious play does a pretty good job in the laboratory if you have a weight of about basically about 0.375 weighting of the most recent observation. Okay, and one, before I show you a picture, one comment to make about this is that this dynamic, weighted fictitious play defines a dynamic learning process, and the rest points of this dynamic will be what are called Nash equilibrium points. Okay, and if the sequence of probabilities that this process defines, if it reaches a limit, okay, that limit point, that attracting point, will be what's called a strict Nash equilibrium. And a strict Nash equilibrium is the way I define a convention. Okay, and I'll again give you an example in a moment, but strict Nash equilibria are just simply points in a game where if any of the agents basically were to deviate by herself, she would actually lose, her payoff would actually drop. And so it's a particularly stable point. Okay, and so bringing back the chocolate cake problem, right, here is a summary description of the chocolate cake game, which is basically, this game has a particularly simple structure where it's quite simply this, is that Claudia and Laura are the two claimants, and each of them receives a payoff that is simply defined as the amount of chocolate cake she receives. So it's a purely linear payoff, very simple in amount of chocolate cake that you get on your plate. Okay, and so there in this game, basically, there are two pure strategies that Claudia and Laura can follow at first. Okay, the first being, all right, if you can follow the strategy M, which is modest, and you claim nothing, if it's going to come back. Or you can follow the strategy G, which is claim everything. Okay. All right. So in this chocolate cake game, it turns out that there are 3 points in the game that are what we call Nash equilibria. Okay, and I've actually shaded them for you. Okay, one of them is where Claudia's greedy, Laura's modest. One of them is where Laura's greedy and Claudia's modest, and the third is where both are greedy. Okay. Now, by the way, I don't know how much this might be new to some people, but just to be clear, okay, in each of the cells, okay, all right, there's a payoff vector, okay, and the left-hand payoff is Claudia's payoff, the right-hand payoff is Laura's. So at the outcome G and M, okay, Claudia's payoff is 1, she gets all the cake. Laura's is 0 because she gets none. Okay. Now, all right. Why are these shaded points Nash equilibrium points? Okay. It's because at any of these 3 points, right, neither player can gain by deviating unilaterally. All right, so one other thing, okay, you notice that I shaded the greedy point dark blue. Okay. The reason I do that is that's one of the Nash equilibria, all right. Okay, Claudia can't do better by unilaterally going from G to M, and neither can Laura. Okay. You notice they both get a payoff of 0. Okay. So question, why on earth would either of them actually opt for the greedy strategy? Okay. Because if they both do, they both end up at a strictly suboptimal equilibrium. It's like, well, why would they do that? Okay. Well, if you look at it, okay, the strategy in this chocolate cake game of G is what is known as weakly dominant. Okay. And by that I mean, basically, that, all right, from Claudia's perspective, okay, if she follows G, she always does at least as well, no matter what Laura does, as if she follows M, and at least one possibility, Claudia does strictly better. So basically it's, and similarly, Laura's strategy of following G is what we call it's weakly dominant. Okay, Laura can never do worse, and at least one outcome she'll do better. Okay, and so on the surface it looks like rationality recommends for both of them to follow G, and guess what? They both do what's allegedly rational, and they both get nothing. Okay. So what I did to illustrate the weighted fictitious play process, I got 2 pictures. Here's weighted fictitious play applied to the chocolate cake game for only 1 orbit. Okay, and darn it if I can get that thing to come back to me. All right, so I can't get the pointer to come out, but the initial point in this example basically is that Claudia has an initial probability, an initial conjecture that Laura chooses modest that's about 0.7. Okay. Laura has an initial conjecture that Claudia chooses modest, that's about 0.5. Right? What they do then is they start with those initial conjectures. Each one of them chooses the best response given her probability, and then you see where the second point is. The second point, after they update their conjectures one time, now Claudia's updated conjecture is that Laura will follow modest with probability only 0.2, because in that first round, okay, Laura didn't follow M, she followed G. And likewise, Claudia's conjecture that Laura follows M goes down to about 0.15 because Laura just followed G, all right? And you see actually where this sequence of conjectures is converging. It's going to that 0.00. Okay. That's the point at which both of them believe that the other follows M, modest, probability 0. And consequently, they both believe the other follows G with probability 1. Okay, so this left-hand corner point corresponds to the G equilibrium. Okay, and then one more picture. There we go. Okay, now 100 orbits of weighted fictitious play applied to this chocolate cake game. Okay. You see where, all right, it looks kind of like a little bit like almost like the feathers on a flamingo bird, right? That you got like all the different upper right hand dots. Those all correspond to initial conjectures that are chosen in the simplex at random. Okay, every one of the orbits goes boom to 0 and 0. So what you have here, this is an example. Okay. In this chocolate cake game, G is what I call, it's what's known as a global attractor of inductive learning, which isn't all that surprising, right? So the blue bar here corresponds to basically, you run in this case I ran just 100 orbits for just 100 different initial conjectures, and 100% of them correspond to that blue bar, that number 2. That corresponds to all of them converging to the 0-0 equilibrium. None of them go anywhere else. Okay, so very, very boring distribution, but just to illustrate the process. Okay. Now here, what I wanted to do is to apply this kind of inductive learning to the bargaining problem, where now the strategies are enriched so that the agents in the game can claim fractional shares. Okay? If you allow the agents to claim fractions of the good, then they can do a whole lot better, even in a game like this chocolate cake game I just did. So, right. I'd be very happy to share the source code with anyone who's interested. I did these simulations in MATLAB. Okay, which is just absolutely wonderful, in my opinion, for simulating learning in games of the like. And what I did was I basically allowed, in each of the games I'm going to show you now, I allowed what we call a claim precision of delta is 1/100th. So in other words, the agents in Claudia's and Laura's positions, each of them can basically claim a share that's a fraction of 100, okay? Basically, that each of them has available 101 pure strategies that go from claiming 0 or 1/100th or 1/50th or so on up to claiming everything. So the resulting strategic form game, basically, you don't want to see it, all right? I wouldn't even hope to try to construct it. It would have 10,201, that's how many cells would be in the corresponding matrix. So it'd be a very, very big matrix. It's, okay, but basically, so that's why, I want to mention, by the way, that in order to analyze these bargaining games, it has to be done computationally. So in other words, these basins of attraction, like I showed you a minute ago with the 2x2 chocolate cake game, they can only really be done analytically, basically, for cases at most having 3 strategies, because beyond that, even 3 strategy games, it can get very, very hard, if not impossible, to identify the attracting regions of the belief simplex analytically. It has, but it can be estimated computationally. Okay, and so I'm bringing back the chocolate cake game. But now, okay, Claudia and Laura's options are enriched. And if I can get the darn pointer to show me anything, that would be nice. Right? So the green region now corresponds to them being able to claim shares of the chocolate cake. And basically the dot that's on the line that's in the middle, okay, 0.5, 0.5, that dot is the equilibrium solution where they each claim half the cake. And in this game, okay, that also, that point is exactly the same. It's a point where the Nash and the Kleist, Mordetzky, and the egalitarian solutions, they all overlap and coincide. So here's a distribution. So I'll just explain this one in detail and show you the other examples quickly, because I know we're running short on time. But to tell you how these are done, okay, I ran, okay, basically simulations that were where you had the agents would basically begin with an initial prior probability distribution, and they would learn according to weighted fictitious play, and I would allow them to run for 200 cycles, okay, which is enough time for them to reach a limit if they're ever going to reach one. Okay, I did this 100,000 times. Okay, so this distribution corresponds to 100,000 rounds of the agents playing the chocolate cake game. At each of those 100,000 rounds of play, basically their probabilities are reset, their prior probabilities are reset at random, and you see what happens. Okay, 0 basically corresponds to the point where Claudia's greedy and Laura's modest. 1 is where Laura is greedy and Claudia's modest. The red arrow is equal division. See? In this example, okay, the conventions that inductive learning lead to, they basically are centered around equal division. Not really any big surprise, but nice to see. Okay. And then we move on to more interesting games. Okay. So this game right here, this triangle, I call this game the Gaudier game for probably obvious reasons. David Gaudier presents this in one of his books as an example. All right, and basically this game can be thought of as basically a hybrid game where Claudia has the payoffs of the earlier chocolate payoff game, but Laura's payoffs are, I'm sorry, Laura, it's reverse, sorry, that Laura has the chocolate cake payoffs. Claudia's payoffs are a little bit different. Okay, so that Claudia's actually, her payoffs basically are 1/2 instead of 0 when she gets nothing and Laura gets everything. And the feasible set is defined by this triangle. And you see that basically the Nash solution is the top of the triangle, the top vertex. That's where Claudia gets no cake and Laura gets all of it. And then the egalitarian and Kleist-Mordetzky solutions basically are that 1/3, 2/3 point. Okay, and Gaudier presented this example to try to show that his favorite solution concept, Kleist-Mordetzky, was better than Nash. Okay? And so I ran it against the Gaudier game. Oh, and by the way, what you have here this time, all right, is that you see how I've got another distribution of outcomes. All the simulations are similarly structured, where they all basically, you have 100,000 runs of play of 200 cycles each. So that there's basically a lot of data to work with. And this time the distribution of resulting conventions, it looks basically like it's close to the center of the distribution looks close to egalitarian or Kleist-Mordetzky. Oh, and I should have said before, everyone, So you might say, well, what if anything is new about all this analysis? Right? That basically other forms of learning that have been analyzed in the literature, they have seldom been applied to the bargaining problem. And the reason for that is because the bargaining problem typically has asymmetric payoffs, like the one in the Gaudier game right here. And learning rules are not very easy to apply to asymmetric games with asymmetric payoffs, and so they haven't been done all that much. So as far as I know, I'm the first to actually look at bargaining problems with payoffs this asymmetric. Okay. A third example, which is also, all these examples, by the way, have been studied ad nauseum in the game theory literature. I call this example the false mirror. Okay. And then this is a game where the payoff region looks like it's rectangular in shape, and on the surface it looks like, because it's the payoff, the feasible payoff is this nice symmetric rectangle. You might think on the surface, well, where should the most natural solution be? Okay. And you might think, basically, that it's that 13-16, 13-16 point where each side gets an equal share. Okay. But I call it the false mirror because if you look, in fact, there is an asymmetry in this game, and it's the asymmetry occurs at the MM and the GG outcomes. Okay. And so it's not really like the game is a real mirror image of, and so, right, the Kleist-Mordetzky solution of this game I've drawn up here is 0.769 and 0.856. The Nash solution and the Egalitarian solution basically coincide at 5/8 and 1. And boom, okay. When I apply the inductive learning to this game, you see that the strongest attractor this time looks at the Nash egalitarian solution. And guess what? Thankfully, everyone, only one more example and I'll be done, because I know we're tiring and I've carried on quite a bit. All right, the last example here. This is the Braithwaite game, which has appeared several times. This game, like I've said before, it's generated its own literature. It's like, and it looks so innocent on the surface, because see, the lower left is the matrix defining the extreme payoffs of the Braithwaite game. And you might say, well, how could this game be so recalcitrant and so hard to analyze? Well, one reason why this game is of interest is that this is one game that's fairly simple, where the Nash and the Kleist-Mordetzky and the egalitarian solutions are all different from each other. Okay? And I said before, right, that the Nash solution, you can see a second time, the Nash solution is very biased towards Laura. And so for that reason, some people have thought, well, there's got to be something fishy about the Nash solution, right? But what happens when we apply inductive learning? Okay, and so I tried doing just that, and basically, pictorially, it looks to me like basically the best contender, if you will, like which of the three solutions, if any, is the best attractor for the Braithwaite game. It looks to me like it's the egalitarian solution again. Okay, so end of examples, and then, so what, if anything, do we get from this kind of analysis? And so, first of all right, I think that inductive learning, it can basically generate a variety of distinct conventions, which is, I think, the way it should be. I don't think we should require that there be deterministic solutions to the bargaining problem. But at the same time, I also think some bargaining conventions might be more likely to emerge than others. And this might basically give, again, some computational support to the egalitarian solution that I think has been neglected. Okay. I also think, basically, in my opinion, this basically suggests maybe we should revisit this question about admitting interpersonal utility comparisons into the analysis of bargaining problems. And then there's also basically, like I said, in my opinion, this suggests a focal point explanation for the Aristotelian principle that Aristotle believes everybody agrees upon. And then last slide is just possibilities for future work. Okay. One thing that I haven't succeeded in doing because of my relatively weak programming abilities is applying this kind of inductive learning to bargaining problems with 3 agents. I mean, I'd love to know what the results would be then. The one thing I've already started looking at are applying this kind of inductive learning to asynchronous bargaining problems that are, so basically, these are more famously known as ultimatum games, but this is where you have 2 agents. One of them basically proposes a division and the other either accepts or rejects it. Okay. I think that this potentially opens the door to trying to confirm any of these results with laboratory experiments. And then again, I think that means that perhaps there's more work to do on trying to compare utilities across individuals, but that's probably a good ending point.